So, in the last lecture we have read the definition of ring and mainly the differences of the other algebraic systems like semi group, monoid group, where the set a non-empty set we have considered with one binary operations defined on it, and then what are the axioms are satisfied by this set with these operations. Ring is mainly different from other algebraic systems because it involves two binary operations on the non-empty set, and we have read the what are the properties that it must hold. There we have the two binary operations we have called the addition and multiplication, but that are not always the ordinary addition and multiplication. It may be ordinary addition or multiplication. So, first we will see one such example, that where the operations are two binary operations, but not our ordinary addition and multiplication. So, first we consider the ring examples. That means, one example with two binary addition operations which are not ordinary addition or multiplication. So, we consider one example that is let us say R is a ring, R is a, or better I write R normally the way we write R. I give two operations like that. So, let R, I am telling plus dot be a ring or initially I take that it is an algebraic system. With the two binary operations defined as follows, because I am not taking these are ordinary addition or multiplication. So, what are those operations? The operations I am taking, that one addition I am defining that A addition B is A plus B minus 1. Here this right hand side of the equation in RHS plus and minus are ordinary addition and subtraction. Ordinary addition and subtraction. and the multiplication we defined A dot B is A plus B minus A into B, AB, that means multiplication. So, similarly in RHS plus minus and better I give a dot and dot R ordinary, addition, subtraction and multiplication. So, here the plus and dot within circle we are taking two binary operations. The operations are defined like that. So, they are not simple ordinary addition or multiplication, but it involves some addition, subtraction and multiplication. Now, we check whether this algebraic system becomes a ring or not. So, check if R plus dot if the algebraic system is a ring. So, if we remember the properties of ring, so one by one we try to check that thing. Okay. So, we give the solution and this is a continuation. Now, first the closure. So, the closure with respect to addition. So, here addition is this addition. So, this involves these operations involves ordinary, addition and subtraction. So, the closure property holds, that is that if AB belongs to R, then A plus B equal to A plus B minus 1 belongs to R. Now, we see that associative property. Okay. So, this is my, I write this is closure. Then we see the associativity. So, if ABC belongs to R, first we see that A B plus C, this becomes A and this part is A plus b plus c minus 1, b plus c minus 1. Again if we apply, we will be getting a plus b plus c minus 1 minus 1. So, this becomes a plus b plus c minus 2. Now, if we take a plus b first and then c, we will be getting a plus b minus 1, c is a plus b minus 1 plus c minus 1 is equal to a plus b plus c minus 2. So, these are equal. What we see that these two are equal. So, the associative property holds. Associativity, the property holds. Now, additive identity, we see the so, if say some z exists such that a plus z equal to a equal to a, then z is the additive identity, then z is the additive identity. So, if I write a plus z, so a plus z equal to a, which implies that a plus z minus 1 equal to a, that is z equal to 1. So, 1 is the identity of or additive identity. So, 1 is the additive. So, we notice that here this addition in a circle is the addition operations we are assuming is the additive identity. Now, what about additive inverse? So, if we remember the our definition that if I have some element, say inverse element, so that A addition A dash equal to my identity, and identity becomes 1. So, what is A A dash for some, we have to check whether some A dash exists or not. For some A dash belongs to R. So, here A plus A dash minus 1 equal to 1. So, A dash equal to 2 minus A. So, 2 minus A is the additive inverse. So, obviously, for each A belongs to R, 2 minus A belongs to R and it exists. So, the additive inverse also exists. So, we have seen the closure, associativity, additive identity, additive inverse. Now, we have to see the commutativity with respect to the addition. So, we see the commutativity. With respect to addition. So, A, obviously A addition B equal to A plus B minus 1 equal to B plus A minus 1 equal to B sub A. So, it is commutative. So, it is commutative. So, we get that up to this property we holds, it is a additive. So, R is an additive commutative group. Since till this time we have considered only one operation and that is this addition, commutative group. Now, I have another operation is multiplication. So, now we check the multiplication properties or the properties with respect to my multiplication. And again we notice that this multiplication is not the ordinary multiplication, it is actually A multiplied by B means A plus B minus A B, and that A B is my normal multiplication or the product, normal product. So, if we remember now with respect to multiplication, we have to check the first the closure. So, this is closure with respect to multiplication. Closure with respect to multiplication, then if I take that A, now this time this is my multiplication is A plus B minus A into B. So, since A B belongs to R, so this is normal ordinary addition and subtraction and multiplication. So, A plus B minus A B belongs to R, because plus, minus and dot are ordinary addition, subtraction and multiplication. Now, what about my associativity? Or I can write associative properties with respect to multiplication. With respect to multiplication. So, we write A C, this is equal to A, this is B plus C minus B C equal to A plus B plus C minus B C minus A normal multiplication B plus C minus B C. So, this becomes A plus B plus C minus B C minus A B minus C A plus A B C. Now, if I consider the ordering of multiplication is changed, that means A dot B first, then a multiplication C. So, this becomes, if we check, this also becomes A plus B minus A B C, which gives that A plus B plus C minus A B minus B C minus C A plus A B C. So, we see that these two are equal. So, associativity holds. Now, what is my distributive properties? With respect to the addition and multiplication defined. So, we can write that this is, since multiplication is distributive over addition. So, this we can, where A B C belongs to R. So, I can write A and this becomes B plus C minus 1. This is equal to A plus B plus C minus 1, because A plus B minus A B plus C minus 1. So, this becomes two A plus B plus C minus A B minus A C minus 1. Now, we see the, if we do the A dot B, this becomes A plus B minus A B. If we take the A dot C, then this becomes A plus C minus A C. Now, if we these two, if we add, that means A B plus A C. So, this becomes A plus B minus AB plus A plus C minus AC minus 1, because my addition is A plus B minus 1. So, here this is A, this is my A, this is my B. So, this becomes 2A plus B plus C minus AB minus AC minus 1. So, again we see that these and these, they are equal. So, the distributive properties. Hold. So, it becomes a ring. So, R, this algebraic system is a ring. Now, whether it is a commutative ring or not, now over ring, if I add the commutativity with respect to multiplication. So, this is if I take A B belongs to R. So, this A B is A plus B minus A B equal to A plus, or I can write B plus A, same thing. I can write B plus A minus B A equal to B A. So, it is commutative. So, it is a commutative ring R Now, if we add the if we see the multiplicative identity, we check whether it exists or not. Multiplicative identity. That means, I have some A dot Z, if I take that type Z exist, equal to A equal to A. So, A plus Z minus AZ equal to A, since already commutative. So, Z into 1 minus A equal to 0, and this is for all A belongs to R. Now, see here this becomes 0, that means either Z equal to 1, this is either Z equal to 0 or A equal to 1. Now, see this A equal to 1, that this property should hold for any arbitrary A, not only for 1. So, this should hold for, so I can write that it should hold for any arbitrary A belongs to R and not only A equal to 1. So, that means that is Z equal to 0. So, my multiplicative identity is z equal to. So, multiplicative identity exists and it is 0. Multiplicative identity is 0. So, the properties that we see that it has multiplicative identities also exist. So, in this way we can check that it is a ring, it is a commutative ring and with a multiplicative identity exists. Now, we see some properties of. So, here some example we have studied that with addition and multiplication, which are binary operations, but not the ordinary addition or binary multiplication. Now, we see some properties that we call the ring properties. Now, we have defined ring with two binary operations. Now, this we can write that in any ring R plus star, telling as if some addition and multiplication. The properties are that one, we can write the 0 element for addition, because we know that 0 is the additive identity. So, if I write that 0 element is E, I write the additive identity is E, it is unique. Same way I can write the additive inverse. So, E is the additive identity. The additive inverse is unique. How I can prove? Okay, I give a proof. The proof is very simple. So, for A part, let there are two, let there exist two additive identity. Say E1 and E2. So, if some A belongs to R, so then A plus E1, that means I can write, if I consider that E2 is since it is identity, that means E1 and E2 both belongs to E1, E2 belongs to R. So, I can write E1 equal to, since E2 belongs to R means another element of R. So, I can write this is E1 plus E2, since E2 is the identity element. Since E2 is identity, additive identity. Similarly, I can write E2 equal to E2 plus E1, since E1 is the identity element. So, that means that is E1 equal to E1 plus E2, since it is commutative with respect to addition. So, I can write equal to E2 plus E1 equal to E2, that is E1 equal to E2. So, the for A part we see the multiplicative identity is unique, additive identity is unique, this is addition. Additive identity is unique. Now, what about the additive inverse? That we can write that for additive inverse, that means my B part. So, for A belongs to R, suppose there are two elements. Similarly, I can take two elements B belongs to R, or I can take two elements B and C. I can take two elements B and C belongs to R. Such that A plus B equal to B plus A equal to E. The identity similarly A plus C equal to C plus A equal to the identity. So, if I write, so B equal to B plus E, since it is a inverse, equal to B plus, I can write E is my A plus C. So, this becomes B plus A plus C. Now, my B plus A is E. From here, B plus A equal to E. So, this is E plus C equal to C only. So, that means B equal to C. So, again that means that my additive inverse is also unique. Now, we can see that subring. We can see that just we can define the way we have defined the subgroup, submonoid, subsemi group, and we can define the subring. So, for a ring R, again plus star, a non-empty set a non-empty subset, say S of R, is called the subring that is under addition and multiplication that means here the plus and star, and as usual that it may or may not be the ordinary addition or multiplication. The R multiplication of R, the restricted to S is a ring. That means that in other words I can tell that with S is a subset of R, then with respect to this addition and multiplication defined over R, that S is also closed and S becomes a ring. So, this is a subring. Then example, I can for every ring R the subsets of identity element is a subring. Or our known example, we see that other algebraic systems we have seen the set of all even numbers, even integers is a subring of Z plus star, where Z is the set of integers or even I can take the set of positive integers. Then also it holds set of positive integers. You can write set of integers. So, there are many such properties of subring and we can write, and some of these one very important property I can tell that or if we consider that examples that earlier we have taken with respect to that, if we remember that one ring, that example we have taken earlier, R that plus dot that ring we have considered, and if we see that whether this becomes a subring or not. Say we are considering that now it is instead of r, that r is actually my z, say r equal to, we consider r equal to the z, and the subset S is set of odd integers, set of odd integers. Then what about the addition, that say A addition B is A plus B minus 1. So, if A B belongs to S odd integers, then this becomes odd. So, this is, that means A B belongs to, so this is, because A plus B is even, so this is odd. So, A B belongs to R, S, A B belongs to S, then A x plus B belongs to S. Then what about the multiplication, that A B is A plus B minus A B. So, if A B are odd, so this becomes even, and this becomes odd. So, this becomes odd. So, I can write that A B belongs to S, A dot B belongs to S. So, we can see that with these two, these are actually holds the closure property. So, I can write that S is a actually subring, S is a subring of Z, here r equal to Z. Okay. So, we have read the algebraic systems ring, and with two binary operations, which is different from the others, repeatedly we are mentioning, and then some examples, mainly to show that the addition and multiplication, the two binary operations that we are defining with ring that are not ordinary, that may or may not ordinary addition and multiplication, and we have read some of the properties and how actually one algebraic systems, whether it forms a ring or not, that we have studied with some examples. So, with this we finish the discussion on the ring. Next day we will see the other properties and how they are related, there are some operations and how they are related with ring.